Hello, hello, hello. Welcome to Hurricane Center Live. This is episode number 148, and today Dr. Phil Klotzbach is going to join us in just a little bit. Always a pleasure to have Dr. Phil on with us, the real Dr. Phil, to talk about beyond just the hurricane seasonal forecast today. I think it's going to be a terrific conversation. Let's thank our sponsors who are with us today, as they always are: USAA, the South Padre Island Convention and Visitors Bureau, LiveView, and the Texas Weather Network, all part of what we do. Let's go to somewhere around Houston and Bill Reed. Bill, good morning. Is that the lake behind your house there?
That's what it'll look like when one of Phil and Hal's massive storm surge comes into my neighborhood. We're probably above where the water will get, but not that far away from where it would. Anyway, I'm up here where the dew point's kind of low this morning, about 73. The dry line must be between me and Hal.
Really comfortable where you are. Hal, you're a little closer to the water. What's it like in Galveston?
Yeah, a little closer to the water here on Galveston Island. Elevation, I don't know, maybe 9 feet this morning. I'm in downtown. Great to join you guys.
Well, it's good to have you along, both of you. Always, Hurricane Center Live is ranked number 4 among natural disaster podcasts. Did you know that by FeedSpot? That's pretty cool, right?
Yeah.
I love that. And if it helps you better understand hurricanes, please follow the show and leave a rating. It really helps improve our rankings. We appreciate that. All right, let's get over to Bill to introduce our guest for the day, and let's get this party started.
Great. Well, I've known Phil since he was tagging along with his mentor and the well-esteemed Dr. Gray back in the day, and he's done a great job of carrying on the forecast tradition. But what a lot of people don't realize is the a great amount of very interesting research that is done on the tropics and other things at Colorado State University. So instead of a forecast talk today, we're going to find out some of the research that our good buddy Phil has been up to out there in the mountains in between hikes. So Phil, welcome to the show.
Yeah, thanks so much for having me, Bill, and thanks so much for having me on this presentation. It does feel weird talking about stuff other than the seasonal Atlantic hurricane forecast. Obviously, we could talk plenty about this hurricane season or lack thereof so far, but I'm going to talk about some other work that I've been up to with a lot of colleagues, including Hurricane Hal. So we're going to actually start with a paper that actually just came out a few days ago. This is some work that I did with Hal and a bunch of other collaborators. And so there's been a lot of work done on, how should we categorize hurricanes? And historically, hurricanes have been categorized using the Saffir-Simpson hurricane wind scale. It's been that way since the early 1970s. But I think there are some potentially metrics that are better for categorizing hurricanes than using the maximum sustained wind. And a lot of this came out of Hurricane Katrina in 2005. So I'm sure a lot of you still remember Hurricane Katrina, horrible hurricane. And when it made landfall, it was categorized as a Category 4. After the season, it actually was downgraded to a Category 3. And a lot of people got up in arms and were like, how on earth could a storm as devastating as Katrina be only a 3 on a 1 to 5 scale? And that's because storms are classified by wind, and Katrina's winds were, while high, were not extremely high, but it had a very, very low central pressure associated with it. And why the central pressure is really important when it comes to hurricanes is because that's why you get winds in the first place, right? It's a difference between the pressure outside of the storm and the kind of the surrounding environment and the pressure in the center. So winds operate off of that gradient or difference in pressure. So if you have very, very low pressures and the winds aren't super strong, that tends to mean you have a very large storm in size. And large storms tend to cause more damage, all else being equal, because a larger storm is going to have a higher storm surge, as well as just a larger area of a larger footprint, say, of wind and rain. And so in the case of Hurricane Katrina, it was an absolutely enormous storm, and obviously everyone remembers the catastrophic levee failures and what happened with that in New Orleans, but also it did generate a 28-foot storm surge, just a mind-boggling storm surge associated with that storm. Whereas on the right-hand side of this figure, we have Hurricane Charlie, a very damaging storm for Southwest Florida, but Charlie, you see its winds were higher, so it was a Category 4, but its pressure was also a fair amount higher. Charlie was a very small system, and even though it made landfall in an extremely storm surge prone part of the Southwest Florida coastline, it only generated a maximum storm surge of 7 feet. So while Charley obviously caused a tremendous amount of wind damage, not much in storm surge damage. And so this is kind of, I think, a good example for why we should consider using pressure as a metric for categorizing hurricanes. Myself and a bunch of colleagues have done a lot of work highlighting how pressure correlates better with the damage. And we kind of hand waved that there was a relationship with storm surge. But I thought, why should we just hand wave when we can actually go and use really good observational data compiled by Hurricane Hal? So thanks so much to Hal for collaborating on this project. So the data that we use, we're actually going back to 1963, and you're probably saying, why 63 is kind of an odd year to start. That's because that's where we have a pretty good, robust data set of direct tropical cyclone fatalities, and we're going to look at fatalities in this analysis as well. We're going to use the observed peak storm surge from HAL, a data set known as U-surge. We're also using modeled peak storm surge from the advanced circulation model known as ADCIRC. And one of the benefits of using this is because in the real world, we get measurements of storm surge in certain spots. So we have where the peak surge was, but to measure the peak surge, you have to have kind of that still high water line, which is hard to measure. It doesn't give us necessarily an overall kind of spatial footprint of the surge, but you can get that from the advanced circulation model. We're going to use normalized damage, which is basically the damage that the storm caused at the time, adjusted to how much damage that storm would likely cause today. Basically take the historical damage and adjust for inflation, changes in population, as well as wealth. So you can think of it as basically the increase in exposure along the coastline. And then direct fatalities. This is a nice compilation that's been recently put together by my colleague Jo Muller and her colleagues at Florida Gulf Coast. These are basically excerpted from the National Hurricane Center tropical cyclone reports and using some other sources where available. So we're going to be showing a few different scatter plots throughout the day. And so here we're looking at our relationship between wind and surge. This is every single hurricane landfall, its peak observed storm surge from HAL's data set, and its landfall. And so you can see there's a pretty good relationship between wind and surge. But if you look on the right-hand side, you see the correlation is improved using pressure and surge. As you would expect, the correlation is inverse because lower pressures mean a stronger storm. So overall, you do get a more robust relationship using pressure relative to wind. And I've highlighted Hurricane Katrina. It falls pretty far off that best fit line for wind versus surge. So Katrina really wasn't particularly well anticipated for just how much surge the storm caused, just using its maximum winds, whereas pressure fits quite a bit better. As a geographer, as I know Hurricane Hal was as well, a lot of, and Bill Gray, my mentor, also majored in geography. I kind of want to know, where do these storms that cause the storm surges, where do they form? And so this is looking at where each storm was first named. So these are color-coded based on the peak storm surge that they generated. And so if we look here, we have kind of three regions where your high-end storm surges tend to develop. One is in the Western Caribbean. As the additional one is in the central tropical Atlantic, and then you have kind of a third category in the eastern part of what we call the Atlantic's main development region, where hurricanes tend to develop and intensify. One thing I want to draw your attention to is if you look in the Gulf, obviously there are a fair number of hurricanes that first get named in the Gulf, but those tend to not have these really high storm surges. Couple of reasons for that. One, storm surge is kind of an integrated metric. It's kind of like the long push and the fetch that you have with the water. So when a storm forms and makes landfall pretty quickly, that storm just isn't going to have quite the long fetch of winds that you would get for, say, a storm that's been out there for quite a while. In addition, storms tend to grow in size with time. So often storms, say, that form in the Gulf aren't necessarily going to be particularly large in size, so not necessarily going to have as much of a surge threat. So not to say these can't be highly impactful storms, but probably not going to be the huge storm surge drivers. Tend to be storms that cause the big storm surges tend to form a little bit farther away from the U.S. coast. Here what we're looking at is a relationship between storm surge and damage. And so here we rank the surges and the damage. And the reason we do that is because we know there's some really huge damage events, say like Hurricane Katrina in 2005, Hurricane Harvey in 2017. So those tend to kind of swamp the signal. By ranking them, you kind of diminish some of that really high impacts that you get from individual outlier events. And so you do see, obviously, when you get higher surges, you tend to get more damage. And it really starts to jump out as you shift towards these really high-end damage events. So on the right-hand side, what you're looking at is basically like a box and whisker plot, so showing kind of how the medians and the distributions change. Now, one thing that we know is obviously, this is just looking at the kind of the basically the physical impacts of the storm. Obviously, this analysis isn't taking into account where the storm made landfall. And we know it's all about location, 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 right? Like if a storm makes landfall and is a massive storm, but it makes landfall in the middle of nowhere where nobody lives, its damage isn't going to be nearly as high as, say, a weaker storm making landfall in a densely populated area. So the fact that you get these pretty robust relationships without even knowing where these storms are making landfall I think is pretty impressive. What I wanted to do next was look at some regional relationships. So here what we're going to do is split the Gulf and the eastern seaboard. And so these black lines kind of delineate the two regions. So the Gulf basically tends to be where your peak storm surges occur. On the eastern seaboard, using our definition, basically you have two greater than 4.5 meter storm surges. You have Hurricane Andrew in 1992 in South Florida, and then Hurricane Hugo in central South Carolina. So we're going to look and see how these relationships work for the Gulf Coast as well as for the eastern seaboard. And if we look at the relationship for the Gulf Coast, you see pretty similar to kind of broadly what you get overall. There's a little bit of more scatter for wind versus pressure. So pressure, again, works better at categorizing hurricanes. But we really see a pretty marked improvement for the eastern seaboard. You see a pretty broad spread in the surges versus for wind, whereas for pressure, it fits a lot better. And a lot of this is that, I grew up in the Northeast US and Massachusetts. And so these storms, as they get into higher latitudes, they tend to expand in size. And so the maximum winds aren't necessarily a great measure of kind of the damage that these storms may cause. You really want to look at the pressure, because sometimes these storms are kind of big and sprawly, and they may only have, say, 80 knot winds, but they may have a pressure of like 950 millibars and be huge surge events. So I would argue that, kind of your typical Category 1 hurricane in Texas is going to be very different potentially for a Category 1 hurricane making landfall, say, in North Carolina or New York. One thing I like to talk about is if we look at the state of North Carolina, if you assume the Hurricane Hazel made landfall right in the South Carolina-North Carolina border, but if you call that a South Carolina landfall, since 1900, there's been only one major hurricane by wind in North Carolina. So obviously, there's been a lot of storms making landfall in the Carolinas with pressures in the 940s and 950s that would be categorized as major hurricanes on our scale, which uses 960 millibars as our threshold between Category 2 and Category 3. So I think this is giving additional evidence that we really should be considering using pressure when categorizing hurricanes. Now, when it gets to fatalities, obviously the relationship gets fairly messy, and some of that's just due to the fact that a lot of storms have, say, 0 or 1 fatality, and it's kind of, you can have storms that are pretty strong, pretty weak, thankfully causing few fatalities. But as you go towards higher intensity storms, you do see that, as the surge gets a lot higher, you do see a much significant shift upwards in the odds of high fatalities. Now, obviously, we're looking at these events since 1963. Since 63, we've had a large growth in population along the coastline, but at the same time, we've obviously have much improved forecasts, much improved warning systems, better evacuations. So, thankfully, per person along the coastline, the odds of dying in a hurricane are much, much lower than they were in the 1960s. So when we're looking at these relationships, you do have to take into account that, we're obviously do a lot better job at forecasting and messaging now than, say, we did in the 1960s, just obviously given the tremendous technological improvements that have occurred since that time. One last plot on this research. This is just highlighting the odds of getting a storm with more than 30 direct fatalities by the peak storm surge. And so, if you have a very low surge, the odds of having a lot of people dying are quite low. The only storm that had a lot of fatalities when it had a very low storm surge was Hurricane Inez in 1966, which sank a boat basically right offshore. And obviously, as you get to these really high-end storm surge events, you do see a much increased chance of a large number of direct fatalities. We also do find that the modeled surges and the peak storm surges match up pretty well. There is some spread, but they match up quite well, which I think is good news because obviously, again, observed peak storm surges takes a long time after the fact to maybe get those measurements. And again, doesn't give us maybe as good an idea of, say, the overall footprint of the storm surge that we can get from a model such as AdCirc. So we're pretty happy to see that these results match up fairly well. And also, in addition to looking at the levels of the peak surge, we also looked at where the model said the peak storm surge was, where compared with where HAL found the peak storm surge to be. And they matched up quite well. We had most of them within even about 100 kilometers of each other, which I think is also really encouraging. So, there's a lot of, I think, really interesting research that can continue from this. So just in conclusion on this topic, size certainly does matter. It is very important when it comes to hurricanes. One of the benefits that we also note with pressure is that not only is it a better correlate better, it's also much easier to measure. For example, both on land, it's a lot easier to measure the pressure of a storm with a barometer. You don't necessarily even need to be outside to get the accurate pressure measurement. Whereas wind becomes, as Bill Gray would say, a real can of worms as you move inland. The second the storm moves on shore, those winds decrease. The maximum sustained winds decrease very quickly due to friction. So measuring exactly where those strongest winds are becomes very challenging. In addition, with aircraft, it's measuring the pressure in the center of the storm is a fairly straightforward process. Whereas measuring where the strongest winds are, winds tend to fluctuate a fair amount, even in the same quadrant over time. So it's just a lot trickier to measure the winds than it is to measure the pressure. We think it's really that implicit size component of pressure that makes it an ideal hurricane categorization metric. And it's awesome that we can just measure it effectively with one number. One thing I do point out is that right now the National Hurricane Center measures pressure but does not forecast it. But some work that I've done with colleagues led by Dan Savas shows that pressure, you can forecast it using the radius of 34 knot winds, the maximum sustained winds, and the latitude, which is all information that the National Hurricane Center does forecast. So this is something that we could use in a forecasting sense as well. And so I'm happy to maybe take one question on that, and then I have one other topic paper that we're hoping to submit by the end of this week. So does anyone have any questions on what we just talked about?
Bill, go ahead, or Hal.
Oh, yeah, I was waiting for Hal to jump in there.
Muted, Hal.
Yeah, right here. Phil, I mean, love the research here. It was a joy to work with you on this. I mean, how could this relate to better communication and decision-making along the coast? Like where I live, people say all the time, I only evacuate for Cat 3s. This type of research, how could that maybe reframe some of that thinking?
Yeah, I mean, I think, when you look at, say, a storm like Hurricane Ike, obviously, which was a big problem in, we're in your neck of the woods. And a lot of people said, oh, if it's a major hurricane, I'll evacuate. And it was a Category 2 with 95 knot winds, so one knot short of major hurricane. So some people may not have evacuated because of that. When you look at the pressure of a storm like Hurricane Ike, it was certainly a major hurricane based on our pressure-based categorization scale. And so I think not that pressure is perfect. It's not this panacea. I mean, obviously, you really want to be forecasting each of the individual impacts. But to the general public, if we're going to be conveying one number associated with a storm, pressure, I think, really does kind of get a better kind of the overall suite of impacts that we're likely to expect relative to just the maximum winds in the storm.
Awesome. All right, amazing stuff. I love that. And I know you've got another topic, so let's take our mid-show break very quickly here, and then we'll get on to the next topic because we've got 1,000 questions for each one of them. And go ahead and stop sharing your screen for a moment if you can, and we'll thank our sponsors who are part of the program week in and week out. Thank USAA, the South Padre Island Convention and Visitors Bureau, LiveView, and the Texas Weather Network. Bill, we are into the thick of the hurricane season, and the Atlantic starting to wake up, and the Pacific, that's a whole different ballgame right now.
I think the Atlantic's just rolling over in bed and debating whether to get up or go back to sleep. But I'll give you a couple of things here before we get back to exactly what Phil's talking about. The Atlantic, there are two systems of hurricane centers watching. And oh, by the way, I forgot to mention, this is being pre-recorded for viewing later. These forecasts, don't take them as what's existing. When you watch this, please go to the Hurricane Center website for the most current info. So 95L has got a brief window of opportunity before it's merged with the westerlies, and not something we'll talk about. A lot of interest in 96L, which has now got a likely chance of development as it comes east. But I've read a lot of commentators out there that look at this a lot more detail than I do anymore, and it's got a few obstacles to overcome, and we'll see if it actually gets to that point. Just a brief look at the satellite loop we got in there. This was 95L up in here, getting ready to disappear from the tropical page, and I guess it doesn't want to work. That happens every now and then, so we will go to 95L. And this morning, it actually has a area that looks like there's some potential for circulation, but it's going to stay out at sea and again become extratropical. 96L is the most robust system to come off Africa so far. Most of the convection is on the west and south side of the apparent circulation, which is some semi-exposed up here to the north. What it's going to do is anybody's guess, and I think we'll worry about that later. After that, you start this time of year, we're really looking at Africa for the source of wave activity. It looks, Phil might correct me if I'm wrong, but it looks like it is dry and fairly stable with no significant waves right now coming across Africa. We won't talk about the Pacific, but it's like a fleet of piranhas out there, or pick your storm. The one that hadn't formed yet is the one the models have the most interest in, but it's all out to sea. So at that point, we will get back and we will see what Phil has to offer in Chapter 2.
That's a lot. But before we get back to you, Phil, Hal, you were part of that research, and you're going to talk about that on your GeoTrek update, right?
For sure. Yeah, for sure. It was just so much fun to work with Phil with this. It was just great. And I love how much observed data that was used. But man, Phil is just, he's very assertive with his research project. He's going to go after it and keep on it. And it was just so much fun to work with him and his team.
Awesome. Thank you. Okay, Phil, let's go on to part 2 and then take it away. Share your screen again, and away we go.
Sounds good. I was going to make one comment because I can't not comment on the hurricane season. One thing that's been really interesting with these easterly waves that are coming off Africa is how low latitude they've been. The ITCZ just isn't moving very far north. The intertropical convergence zone has stayed pretty far south. Like this wave that just came off is like 10 north. Usually this time of year, there should be more like 14, maybe 15 north. Bill Gray used to always say, if it rains hard in Dakar and Senegal, that's when you really want it. Those are the waves that you really got to be concerned about at the peak season. So it's interesting. The ITCZ just really isn't moving very far north, which is kind of a typical El Nino sign. And just kind of another sign that probably this season is going to be, fairly quiet overall. So could not comment on that. But now back to this. So yeah, we are going to talk about another area of research that something hopefully going to be submitting this week. It's currently with co-authors. A bunch of them have already gone through it. And so this is taking that tropical cyclone fatalities data set that I talked about briefly earlier, and then looking at how that's modulated by El Nino Southern Oscillation, as well as the Atlantic Meridional Mode. And so some of the reason for this is that, we always emphasize with each of our seasonal forecasts that it only takes one, right? It only takes that one storm making landfall to be a bad day for you. But I do want to point out that, it's not that a lot of fatalities is completely random. In general, busier seasons do have more fatalities. And so just to start, this is a plot of these direct fatalities since 1963. You see basically there's not much of a trend. It's pretty much flat, which I think is really a testament to better forecast, better messaging, because obviously we know there's a whole lot more people and a whole lot more stuff in harm's way now than there was in the 1960s. Huge growth in exposure along the coastline. Bill Gray used to always say it really started to skyrocket in the 1970s because that's when air conditioning became affordable and it became a whole lot more comfortable living in places like Texas and Florida in the summer than prior to that time. To point out, though, there are these 3 years that really jump out for fatalities. You have 1969, most of those from Hurricane Camille, 2005, most of those being from Hurricane Katrina, and then 2024, most of those being from Hurricane Helene. So we want to kind of look and see, what are there climate modes, are things that kind of tip us off to whether the season is going to have a large number of fatalities or not. So really, are they related to large-scale climate, or are they just kind of random? Then we're going to look at a couple of different climate modes. I'll talk more about those in a minute. And then we're going to focus on how about storms forming in the Atlantic's main development region. That's the region where most of the major hurricanes that form in the Atlantic, where they tend to go. And we would think, given especially the impacts that these climate modes have are typically strongest in the tropics, that we would find the impacts on the fatalities, most of them deriving from these storms that form at lower latitudes. So we're going to again use this direct fatalities data set from Joe Muller. We're using the historical National Hurricane Center's best track data set. So it has the tracks and the intensities of all the storms going back all the way to 1851. We're going to use plotted data or observational data from the European Center's latest reanalysis product, which is a really cool kind of representation of what all these different large-scale fields like winds, pressures, temperatures, what those look like every day, going back all the way to around 1940. We're going to use NOAA's new Relative Oceanic Nino Index to classify El Nino and La Nina. This index is pretty cool. Basically, what it does is it takes the water temperatures in the eastern tropical Pacific, the region that NOAA focuses on for El Nino, and then differences from the tropical mean, which helps to kind of remove any signal from long-term warming. And we're going to use the Atlantic meridional mode, meridional because it's in the north-south direction. This index was developed by Jim Cosson and Dan Weimont at the University of Wisconsin, and they still update it today. So to kind of pick our years, you're taking the top 15 and bottom 15 years for ENSO and the Atlantic meridional mode, or AMM. If you're interested, these are the breakdowns. So NOAA's definition of an El Nino is basically half a degree Celsius or more warmer than normal. La Nina is basically minus half a degree Celsius or colder. So just basically kind of right on that threshold, a little bit more dramatic. So we're kind of highlighting, moderate to strong El Nino and La Nina events for AMM. Basically similar. And then we're going to actually combine these as well to look at the impacts of these two indices in combination to really kind of highlight how these different climate modes would potentially impact the number of fatalities that you get. So just kind of a simple composite. Bill Gray was a big fan of compositing. And so kind of a way to start, we're just looking at here, taking the 15 years with the highest fatalities and differencing them from the 15 years with the lowest fatalities. And these two black rectangles, the one rectangle denotes what we call the Nino 3.4 region, which is the region that NOAA uses to monitor El Nino and La Nina. So you can see colder water temperatures there, indicative that La Nina tends to favor busier or higher fatalities, as well as a warm Atlantic favoring higher fatalities. So kind of the typical factors that we would expect drive a busy hurricane season also tend to drive higher fatalities. This is looking at water temperatures. We also want to focus a lot on vertical wind shear. Vertical wind shear is a change in wind speed and direction with height in the atmosphere. Too much shear is good for us, bad for the hurricane. It tilts the hurricane circulation. It doesn't allow for the pressure fall that you need to get the winds to accelerate. It also tends to mix a lot of dry air into the storm. And so you can see in general in higher fatality seasons, lower levels of vertical wind shear. So again, highlighting that, as you might expect, in general, busier hurricane seasons tend to have higher levels of fatalities. So we're going to focus on two different modes. El Nino is a huge one. You probably have heard about it, discussed a lot about the 2026 Atlantic hurricane season. El Nino, right now we have a very strong El Nino event. Strong El Nino events can have really big impacts on Atlantic hurricanes. And so this is a relationship that Bill Gray discovered back in the early 1980s and really got us into the seasonal forecast game in the first place. And why what's going on in the Pacific Ocean matters for Atlantic hurricanes is what it does to the tropical circulation. So El Nino, again, warmer than normal water in the eastern and central tropical Pacific Ocean. Why this matters for the Atlantic is, in general, in the tropical Pacific or in any ocean, your thunderstorms, your strong thunderstorms are going to form where the waters are the warmest. In an El Nino, those really warm waters shift eastward, more towards the central tropical Pacific. In response, your strong thunderstorms shift eastward as well. Dr. Gray used to also talk about the in, up, and out circulation of thunderstorms. So you have low-level winds that converge in those thunderstorms. The air goes up in those thunderstorms. It spreads out high up in the atmosphere, and that's really how it drives Atlantic hurricane activity. Because when you have that air spreading out in the central Pacific, it really tends to increase upper level westerly winds in the Atlantic, really ramping up your vertical wind shear. And for example, the last 30 days, vertical wind shear in the western part of the main development region has been the strongest on record, going back to the late 70s, again, indicating when you get these strong El Nino events, it really is a huge driver of shear. One of the reasons why the hurricane season this year has been so quiet. La Nina tends to reduce your shear and overall then produce conditions that are more conducive for a busy hurricane season. So what we did first was look at the relationship between El Nino. So El Nino Southern Oscillation, or ENSO, is basically the oceanic component. If the Southern Oscillation is the atmospheric component, so getting into kind of that in, up, and out circulation you get in the atmospheric response. So here we're looking at our box and whisker plot, so showing the distributions of the fatalities. So the line in the middle is the median, the white triangles are the means, and then the whiskers are the 95th to 95th percentiles of these distributions. And you can see that in general, you do see more fatalities and especially more tropical cyclones causing direct fatalities in La Nina relative to El Nino. So obviously you can get significant hurricanes with a lot of fatalities in El Nino, but the odds do certainly favor more fatalities in La Nina. In this paper, we didn't spend a whole lot more time looking at neutral cases, but obviously you can see neutral, there's a huge distribution, right? The median goes down a bit, but there's a big distribution shift, highlighting how just, kind of anything goes in a neutral year. So when you have neither El Nino nor La Nina, likely indicating then, if that's the case, that what's going on in the Atlantic becomes extremely important. So what we did next was look and see, again, kind of that geographical focus. Where are these storms that are causing direct fatalities? Where are they forming? And if we look at El Nino years, we see that, you see kind of a shift in that distribution, right? Where storms tend to form more at higher latitudes preferentially than in La Nina. And so, for example, if we compare here, we compare La Nina to El Nino, we see that there's about 2-to-1 difference in the number of TCs causing direct fatalities, but the number of tropical cyclones forming in the main development region, it's over 3-to-1 difference. So really highlighting how this distribution shift, or basically where the storms that are causing the fatalities is coming from, the big differences we get are from storms forming in the main development region, just not very many in El Nino when compared with La Nina. And keep in mind, we have 15 years in both samples, so we have the same number of seasons going into each of these distributions. As you might expect, La Nina has a lot lower shear than does El Nino, obviously verifying what Bill Gray showed over 40 years ago. And if we, again, focus on just what's going on in the deep tropics, so in the main development region, we do see more significant kind of distribution shifts in La Nina relative to El Nino, as well as for storms forming in the main development region. You see more pronounced distribution shifts. So again, highlighting how these relationships are pretty pronounced, but especially for storms forming in the main development region. We did a similar analysis with what's called the Atlantic meridional mode, and meridional so named because it's what goes on in the north-south direction. So a positive phase of the Atlantic meridional mode tends to be associated with busier Atlantic hurricane seasons. You have a warmer Atlantic, warmer northern tropical Atlantic, more fuel for storms. You tend to have weaker low-level winds out of the west that help kind of spin up storms, as well as reduced levels of vertical wind shear. So you can think of this positive Atlantic meridional mode as generally being very favorable for Atlantic hurricane activity, enhanced rainfall in places in West Africa, again, favoring more robust African easterly waves, or basically seeds for potential development in the Atlantic. If we look at these similar box and whisker plots with the AMM, we also find pretty robust differences. I'd say even a little bit stronger than what we found with El Nino. So you do see pretty pronounced shifts in these distributions, both for the overall number of fatalities, as well as the tropical cyclones causing direct fatalities. We did a similar analysis here to what we did with ENSO, so looking at storms forming again in that main development region. And when you look at this, obviously you can see, if you had to pick which AMM phase to be in, you'd obviously want to pick negative if you're looking for, less likely impacts. Obviously, especially in the main development region, we look at 25 in the positive AMM versus only 5 in negative AMM. So not that you can't get significant impacts, but certainly when you have a warm Atlantic, northern tropical Atlantic, that really does favor more significant impacts from tropical cyclones and more fatalities. Kind of similar to what we see with El Nino, the shear signal is pretty robust as well. Reduced shear in the Atlantic when you have a positive AMM. And so overall, we do find that we see a lot fewer fatalities for storms forming in the main development region, as well as a number of storms forming in the main development region when the AMM is positive relative to negative. Again, kind of like we saw with El Nino, the neutral phase tends to be a little broader distribution, highlighting how, especially say you have a neutral ENSO and a neutral AMM, that was probably a key chance where you actually have a little bit less predictability, both just in overall seasonal hurricane activity, as well as the number of storms, say, causing direct fatalities and the overall number of fatalities. We do see even a stronger relationship when we combine the two. So if we say negative AMM and El Nino versus positive AMM and La Nina, you get a 7-to-1 difference in the main development region. So obviously really highlighting how you do see pretty significant differences, especially if you have conditions that are extremely unfavorable. The odds of significant impacts, a lot of fatalities, are much lower than when conditions are extremely favorable. And as you might expect, when you combine these two modes, you get really strong shear differences, especially in the Western Atlantic. Caribbean becomes a lot more conducive when you have La Nina and a positive AMM. So if you think about a year, say like 2020, where we had a La Nina and a very warm Atlantic, obviously extremely busy in the Western part or in the Caribbean that year. One final box and whisker plot, when you combine them, obviously you see really pronounced differences. So again, highlighting how when all systems are go and all systems are really not go, that's when you see your biggest distribution shifts. So kind of highlighting how we can take, say, seasonal forecasts and potentially even say that these can actually cause differences in the number of direct fatalities. So again, these are all odds things. It's not to say that you can't have a season that's completely very, very junky from a climate perspective, say a year like 1983, very, very quiet season, only had 4 storms all year, but I'm sure Bill can talk a lot about Hurricane Alicia that year and all the damage that it caused in a very, very otherwise quiet hurricane season. But in general, when the large-scale climate is TC conducive, we do see increased numbers of direct fatalities with both ENSO, which is Pacific-centered, as well as the Atlantic Meridional mode, which is Atlantic-centered, significantly impacting the number of fatalities. And it's most significant for storms forming in the main development region. And when they're combined, they really are become pretty powerful predictors of direct fatalities. And so with that, I will stop sharing my screen and I'll try to answer any other final questions. But this is work that we hope to be submitting in the next 3 to 4 days.
Excellent. But I guess the question I would have is, this is fascinating work. What future work do you have planned to continue on this line?
Yeah, so when it comes to fatalities, we would like to do more of a deeper dive into individual components. So this basically said, so when you're talking about direct fatalities, these are fatalities that are directly ascribed to the storm. So it's basically kind of like your canonical like storm surge, inland flooding, and wind, and rip current. What we'd like to do is start looking more at, okay, for individual storms, like the percentage of those fatalities that were, each of those causes, and try to kind of get at, I think even with climate modes, there maybe there's, I think maybe inland flooding may have less of a relationship potentially with some of these modes than say like wind or surge, because inland flooding can be from weaker storms. Obviously, you can go back to a storm like Tropical Storm Allison, which was a very weak storm, not much in terms of winds, but obviously a tremendous amount of rain and a lot of inland flooding. And obviously, we can also go back to a storm, the big driver, the big fatality event that kind of was the exception that proves the rule, as Bill Gray would say, was 1972 with Hurricane Agnes, which reached hurricane strength, but most of its damage was when it was a tropical storm, but obviously catastrophic flooding in the mid-Atlantic. So I would suspect inland flooding may be less of a relationship with some of these modes than, say, the wind and the surge components.
Yeah, because some of them were big like Agnes, and some of them were fairly small like Amelia and Claudette, two that I were.
Yeah, so it's and of course, one of the challenges is obviously we want to have a large enough sample size. So we go back to the 60s, but obviously we know that, there's kind of two forces, right? There's more people moving into coastal areas, which increases that threat. But then at the same time, we do have a whole lot better predictions and a whole lot better evacuation planning now than we'd say did in the 60s. So at least right now, those are kind of like pulled opposite directions. So the fatalities trend is pretty flat. But obviously, when you're comparing a storm like Agnes, if Agnes were to make landfall today, hopefully the fatalities would be fewer just because we have way better inland flooding forecasts and things. But obviously, as we saw with Hurricane Helene last year, even with really good forecasts and overall probably pretty good messaging, we still lost way too many people on that storm.
Yeah.
Do you anticipate, Phil, ever including some sort of fatality metric in that seasonal forecast based on this research? It's challenging, right?
Yeah, I mean, I think a lot of it is, a lot of these things are more probabilistic than deterministic. Like, we're not going to say, okay, the odds are, but you just see, like, in general, when you have busier hurricane seasons, you do see that the odds are shifted. So we always say it only takes one, but I think one thing we try to emphasize with our seasonal forecast is that we don't want to make it sound like, okay, it's completely random. Like in a season like 2026, because the shear looks to be so strong that, not to say that we can't have a significant storm, but the odds are significantly down for, catastrophic damage in the United States, especially in the Caribbean, given how strong the shear is relative to, say maybe a year like 2024, or probably also 2027, when we know we're not going to have this El Nino is going to have gone away. That, the odds obviously next year are probably going to be a fair amount higher than this year. So probably not going to be explicitly forecasting, we expect 71 people to die or something like that, but just kind of trying to highlight, kind of what seasonal forecasts and kind of what these large scale climate modes can do and what they can't do. Obviously you see these big spreads in the distribution. So it kind of changes the odds, but it's not deterministic. Like if these conditions are present, you will or you will not have damage or, a lot of fatalities.
Fascinating stuff, Phil. We appreciate you, man. Thanks for all that you continue to do and for doing such groundbreaking research and keeping up the work of Dr. Gray and taking it to the next level.
Thank you.
We appreciate that. Bill, what did we learn today?
Well, I think this is a great documentation of how another metric might be better for categorizing the storm surge, and it's the sea level pressure minimum value of that as a proxy for the size of the storm.
I think that's fascinating. Hurricane Hal left some comments as well. We appreciate that. He had to duck out. He had another meeting to go to. But guys, we appreciate it. Great program today. Dr. Phil, always a pleasure having you on. We sincerely appreciate all you do, buddy. All right. And with that, we're going to wrap it up. We want to thank everybody for being with us. We want to thank you for joining us wherever you are in the world, on the podcast, on the webcast, wherever you may be. We want to thank our sponsors who are with us week in and week out. USAA, the South Padre Island Convention and Visitors Bureau, Live View, and the Texas Weather Network. Next week, Kurt Avery will be with us to talk hurricane preparedness and clean water. That'll be a great show. We hope you'll join us for that once again. Remember, we're the number 4 podcast now for disaster podcast, natural disaster podcast. Let's climb up that ladder. You can help us do that. Thanks to Dr. Phil. Thanks to Bill Reed. Thanks to Hurricane Hal. Thanks to Alex Garcia back in Control Central. Until next week, stay safe. Bye-bye.